Hi, so today I'm going to be showing you a demonstration of the extension to NodeXL that we have done. NodeXL originally displays static graphs consisting of nodes and edges. Overall, visualizations of graphs can be very important. Not only are graphs effective at capturing the content and structure of many different types of data sets, such as road traffic networks or social networks, but they capture them in a visual way. As the human brain is particularly effective at processing visual information, research in computer science has developed a number of visual exploration systems to analyze graphs and networks. In the last 5 years, an increasing part of the research in information visualization has focused on graph visualization. There have been many different kinds of tools introduced to visualize networks, and most of these have been for static networks. We have extended the popular static graph visualization tool, NodeXL. We have allowed it to now visualize dynamic, edge or node-weighted, time-evolving graphs. Okay, so let me show you how our extension works. First, we can import a time-evolving network into NodeXL. So here in the editor, we select Dynamic Weighted Network Source. At this point, we have two choices. We can either import a network from a flat text file into the database, or we can load a pre-existing network directly from a database. The user interface lets the user choose if they want to choose a network with the nodes evolving over time or the edges evolving over time, as well as choose among different types of aggregation. So here you can see that there are 4 types of aggregates to be chosen from: sum, average, maximum, and minimum. Aggregates that are selected will be computed and allow for their future use. And we'll go over exactly what these choices represent in more detail later. Okay, for now, we import a pre-existing network from a database. And there, it's imported. Okay, for this demonstration, we are using a simple road network consisting of 100 nodes and 130 edges across approximately 9,000 time slices. The weights on the edges for this network correspond to the amount of traffic on the roads across time. So here on the left, you can see the graph's dataset stored inside the worksheet. Its structure is contained within the different rows. On the right, we have a graph panel to visualize the network. Clicking Show Graph over here will display the graph. However, it's not laid out very clearly yet. By using another NodeXL feature, we can choose among the various methods to visualize this graph. Let's try the Harel-Koren Fast Multiscale method. And there. Much clearer. This looks much closer to a road network. Additionally, to make it clearer, we can use another NodeXL feature to increase the edge width. Here, let us increase it to a width of 4.0. Okay, now let us visualize the amount of traffic on this road network. This will help us to better understand our network and dataset. In this case, the aggregate that we chose earlier will be important. Earlier, we were allowed to choose among 4 different aggregates: the sum, average, maximum, and minimum. By mapping the edge colors with minimum aggregate, red for low scores, and green for higher, the color red will represent edges with high amounts of traffic, and green will represent edges with low traffic. Okay, and autofill. The traffic is now plotted. Notice how all the edges are red, representing high traffic? This is because we are seeing the network across all time slices at the moment. Since we have chosen the minimum aggregation, this means the minimum edge or traffic weight across all these time slices is being used to represent the overall edge weight. And of course, when looking across all of time, there will be a point where each edge was perhaps having congested traffic. So now, let's change this. Let's look at not all the time slices at once, but instead short snapshots. So here, you can see the graph representing just one time slice. And in fact, we can now animate this. By pressing the play button, we can see an animation of how the traffic evolves across each slice over time. We can change the speed of this animation as well. In this case, showing every 200 milliseconds, a jump of 200 time slices. And there we go. You can see the traffic evolving over time. The red and brown edges are more congested, and the greener edges have less traffic congestion. We can also see the evolution of the network in different time intervals. Let's say in this case, 10 days. So, as you can see, here is the evolution of the network in 10-day snapshots. There are also other features that can be used to filter and modify the network. For example, this filter applies a threshold to all the edges. Only those edges with an aggregate sum of their weights that falls between the thresholds set by the sliders will be shown. Now I will show you the most important feature of this extension to NodeXL. This part is used to visualize what we have called sig spot patterns within the network. A sig spot pattern is a connected region of the graph over time that has a score higher than a given threshold. Higher scores mean more significant and anomalous patterns. So this means we can discover different and important congested regions within the overall network. By pressing the button Load Sig Spot Patterns, we will be shown a user interface which lets the user choose between first computing, then loading the patterns, or loading some pre-computed patterns from the database. Let us import some pre-computed patterns. Okay, now that we have imported these patterns, we can see these patterns inside a new worksheet called the Groups worksheet. This worksheet contains the region IDs, their scores, and the time intervals where the patterns are defined. Let's click Refresh Graph. And now, the colors of the edges are linked to the patterns they belong to. So, since we are seeing the network in this time interval, most of the edges are gray. This means there are very few significant patterns within this time interval. Let's change the time interval. We can now see different patterns being mapped with different colors. So, if you want to look up, say, this red one, to see the score of this pattern, we can select it and go to the Edge worksheet and see what region it is from. It is from region 72. So now we can go back to the Groups worksheet, order the groups by region ID, and see what score that region had. Also, you can see that once you select a group from the Group worksheet, the Graph panel will highlight all the edges belonging to that selected group. One other thing, the edges which are colored black are actually associated with overlapping patterns. So in other words, those edges belong to two or more different patterns in the given time interval. Okay, overall, we can sort the patterns by score, and in this way find the top K most significant different patterns within the network across all the time intervals as well. So, for example, you can see that this is the most significant pattern in the overall network. Now, since this pattern extends from the time interval 190 to 216, we can restrict our network to this time interval and graph it. And there is the pattern. It covers a large extent of the network, and all the included edges have very high traffic. On a larger network, we could use the NodeXL features of zooming and scaling to see, for example, by pressing the play button, how the patterns in a small subset of the graph appear across time. Okay, so that's it. Overall, I have introduced this extension to NodeXL, which is able to increase the visualization functionality of this useful tool. It allows for dynamic, edge-weighted graphs to be loaded and visualized, as well as significant patterns to be found within the network. We feel that this extension can be very useful for future researchers, as well as individuals who are interested in the visualization of dynamic and time-evolving networks.